What do you think this Python code prints? If you guessed it would update Alice's email to Bob's email, you'd be wrong. The output is actually this one. We now have two fields, and one simple typo just corrupted our data silently. This is what we call stringly type programming in action. Today, we're going to hunt down these string based landmines hiding in your code. You learn five specific techniques to transform fragile string keys into bulletproof types. By the end of this lesson, you'll have developed a radar for spotting stringly typed code before it causes problems in production. Now, let me define what we mean by stringly typed code. It's what happens when we use plain strings to represent important program semantics. Things like field names, operation modes, or identifiers, instead of creating explicit types. Here's a quick comparison. On the stringly type side, you might see code like request body or cipher.get instance with the cipher algorithm passed in. On the type safe side, you have request.body or cipher.get instance with the cipher mode passed in. The core problem is this: when we use plain strings to represent important program semantics, we're trading type safety for convenience. And that trade off will cost us more than we realize. Remember this key insight: every stray string key is a landmine waiting to go off. Just because you don't see it doesn't mean it's safe. Now, let me show you exactly what we lose when we choose strings over types. There are five hidden costs that accumulate over time. First, we lose static guarantees. When you write the statement, the compiler has no idea what key exists in this object. You're flying blind. Compare that to defining an interface where request.body gives us a compiler guarantee that this field exists. Second, we get delayed feedback. Consider this Python code where we misspelled host with a double S in our configuration. This compiles perfectly fine, but 500 lines later, when we try to connect using config with the correct spelling of host, we get a runtime crash. This typo was introduced early but discovered late, maybe even in production. Third, refactoring becomes a nightmare. Want to rename body to payload? With types, your ID can do it in seconds. With strings, you stuck with find and replace, sifting through 847 matches where most of them are false positives. CSS rules that mention body, comments about any body, documentation that uses embody. Good luck with that approach. Fourth, we risk silent data corruption. Going back to our opening example, when we mistyped email as email, instead of updating the existing email field, we created a new one. The bug remains invisible until someone actually tries to use the email address. This kind of silent corruption is particularly dangerous because it doesn't fail fast. Fifth, our development tools become blind. When meaning is hidden in strings, your development environment can't help you. No autocomplete, no go to definition, no dead code detection, and no refactoring assistance. The tools that make modern development productive simply won't work with semantic meaning buried in string literals. Here's a memory hook to remember this: strings hide meaning both from compilers and tools. Now, let me share a real bug that demonstrates how costly these problems can be. This involves a vanishing email address. A front end developer was creating a user registration payload and misspelled email as email. The backend API was configured to ignore unknown fields, a common pattern for API flexibility. Now, a couple of months later, when John tried to reset his password, the reset email never came. Support escalated to engineering, and the bug took hours to track down because it was silent data corruption. This isn't an edge case, it's the predictable result of choosing convenience over safety. So, next, let's fix these problems. I'll show you 5 techniques ranging from quick wins to complete transformations. Technique 1 is named constants. This is your quickest win. Instead of writing, the silent runtime error type, which gives you a silent key error at runtime, extract the string to a constant and then use that. Now, typos become name errors that can be caught immediately at startup. The pros are clear. It's an easy drop in replacement, and your ID can find all usages. The downside is you can still type the wrong string when creating the constant or elsewhere in your code. Now, the memory hook for this is that constant turns silent failures into loud failures. Technique 2 is enumerations. This technique works well when you have a fixed set of values and need exhaustiveness checking. Instead of using raw strings that are easy to misspell, create an enum. In Java, you'll define a cipher mode that encapsulates the string value. Then use this cipher mode in order to actually get the instance of the cipher. Now you get autocomplete, exhaustiveness checking, and safe refactoring. The compiler won't let you use an invalid cipher mode. Technique 3 is value objects and branded types. Value objects let you attach validation and behavior to your data. Instead of accepting any string for a database hostname and encoding, you create a specific type. Define type encoding and abandon hostname type with a validation and a branded hostname type with a validation function. The type system ensures you can only pass valid values to your database connection function. Technique 4 is structural types. This is perfect for TypeScript projects. Instead of writing, request.body where a typo results in undefined, define an interface that describes your HTTP request structure. Now, request.body is guaranteed to exist by the compiler, and you'll get all the ID benefits that come with strong typing. Technique 5 is encapsulation at boundaries. When you must deal with strings, for example, external APIs, legacy systems, try and contain them. Create a type safe interface for the rest of your code base. For example, create functions like getRequestBody that handle the string key internally, exposing only clear interfaces to your application code. Now, I'm not anti string. There are legitimate times when raw strings make sense, but they're exceptions, not the rule. Exception 1 is if you have small local context. If all uses of the string fit on one screen, live in a single function, and are unlikely to be refactored, strings might be acceptable. Exception 2, external protocol requirements. When dealing with HTTP headers, file formats, or APIs, you need strings. But keep the adapter layer thin and isolated from your business logic. Exception 3, rapid prototyping. Sometimes you need to move fast and can accept the risk consciously. Just remember to pay the refactor debt before scaling and set reminders to clean up the code. Even in these cases, Worst case, prefer constants or wrapper functions to scattered string literals throughout your code base. Now, before you write any string literal that contains meaning, ask yourself these five questions. Is this value part of my domain model? If yes, make it a type. Will this key be reused? If yes, centralize it with constants or enums. Can tooling help me rename it later? If no, reconsider using strings. Am I interacting with external protocols? If yes, confine strings to the adapter layer. And number five, will this survive beyond prototyping? If yes, invest in proper types. This checklist will help you make conscious decisions about when to use strings versus when to invest in type safety. Now, here's the fundamental change I want you to make. Stop thinking is just a string, what could go wrong, and start thinking this string carries meaning. How can I make that meaning explicit? Every string literal is a design decision. The question is whether you're making that design consciously or by accident. When you make it conscious, you can weigh the trade offs properly. Short term convenience often creates long term maintenance burden. The goal isn't to eliminate every string from your code base, it's to use the type systems to make illegal states unrepresentable. It's to turn silent runtime errors into noisy compile time errors. When you must use strings, contain them behind type safe interfaces. Now, let me leave you with the big ideas from today's session. String literals are convenient, but types are forever. The short term convenience of using raw strings creates a long term maintenance burden that compounds over time. Make illegal states unrepresentable. Use your language's type system to prevent entire classes of bugs rather than trying to catch them after they occur. Fail fast and fail loud. Turn silent runtime errors into noisy compile time errors. It's much better to get a loud failure during development than a silent corruption in production. Finally, when you must deal with the chaos of untimed external systems, contain it. Create clean, type safe interfaces for the majority of your code base. Remember our central insight: every string literal is a design decision. Make it a conscious one.